Hello geometry students, this is Mr. Fugay, and today we're going to talk about how to find the sector area and arc length of a circle. To begin, at the top here I have listed about the formulas for the area of a circle and the circumference of a circle, just as a reminder of how we would find the complete area of our circle and the complete circumference of our circle. Once again, I'm going to use this analogy, you'll hear me use this in class, is that I'm going to use the analogy of a pizza pie, okay? The area is how much pizza you have. The circumference is how much crust you have, in the sense of if I were to cut all the crust out of a pizza and lie it out in a straight line and measure it, that would be my circumference. Now, what we're going to do in this lesson is we are going to talk about parts or fractional parts of the area and fractional parts of the circumference. And that's where we're going to allude now to when we talk about parts. We're going to use the term sector area to refer to part of an area, and we're going to refer to arc length as part of the circumference. Now, the way that we're going to measure how much of the circle we want is going to be denoted by a central angle denoted right here. So if I wanted to figure out the area of that red slice that you see there on the screen, I would need to find the sector area. Now, I would need to then ask myself, well, how much or what fractional part do I have? If that theta was measured in degrees, we would say it would be theta over 360. And if we were trying to find it in terms of radians, we would say that that theta would be theta over 2 pi. So it just depends on what unit we're working with. And just to give you a quick example, for example, if we had a circle and we were wanting to figure out a 90-degree angle, a lot of you will see that and go, oh, well, that's about a quarter of a circle. Well, if I take 90 over 360, whoops, that is a weird 3, and you simplify it, you would get the fraction 1/4. And the same thing goes if I have pi over 2 pi, okay? You would get this, pi's cancel, and you would also get 1/4. So that brings us down now to how we find these and a formula that we can create. So the definition of a sector is a part of a circle created by 2 radii and an angle. The sector is a fractional portion of the circle's area, think of it a piece of pizza, and is measured in square units. So notice that when you look at the formula in degrees that we have right here, it's the area of the circle formula. But then what we're going to do is multiply it by the fractional part that we want. And the same holds true for arc length. Arc length is a fractional portion of the circle's circumference and is measured in linear units. Again, think in pizza. This is if I have a slice of pizza in my hand, how much crust am I eating? What is the length of the crust I am eating? You will see that we have the circumference formula here, and then we are multiplying it by a fractional part here in degrees. Now, let's talk about how this will become a formula that we can use in radians. Because the funny thing here, as you'll see, is it's actually going to simplify the equation. So you have your degree formula. If we look at it in terms of a radian, looking down here, it would still be pi r squared. But then now, since we're talking about, and let me denote red as degrees. So I'm going to put a little d there just to remind myself. And then this as a radian. So we would now write it over 2 pi. And if we go over here and we talk about the arc length in radians, instead of talking about the theta in degrees, it'd be radians over 2 pi, just like we mentioned up above here, okay? Theta over 360 would be the fractional portion of the circle in degrees. Theta over, because 2 pi is a complete revolution of a circle, that would be it here. When you simplify this, what's going to happen is the pi's are going to cancel. And so what we create, our area of a sector formula in radians, is going to be, now you'll see here that we have theta over 2. I'm going to actually write that as 1/2 theta. So I'm going to split that apart, and then we'll throw that r squared here in the middle. That is going to be our formula in radians. 1/2 r squared, and if you need to put a little r there to remind you that that's a radian, you can. And then what happens in the circumference, in arc length, is that the 2 pi's completely cancel, and we're left with, now the L does become an S, and I will explain in a minute why. But this will simply just become R times theta. Once again, the R is a radian here, or the theta is a radian. Now, S denotes arc length, and without going into a long reason why, it is a Latin word that for arc length starts with the letter S. So you will see if you Google or jump on any sort of online resource about arc length formula and radians, you will see the S being used. So just something I want you to be familiar with. So what we are going to focus on in this video is using the radian formulas. If you notice, they are a lot simplified here. We will use the radian formulas to help us find the answers to our questions. So let's look at our first example. In this problem, we want to find the arc length and the sector area. I'll denote area of a sector in red and arc length in green. So if we want to find the area, it's going to be 1/2 r squared theta. And in this case, we have the r value is 12. We have the theta value is pi/4. So all I'm doing is plugging those things in. So r is going to be 12 squared. Theta is going to be pi/4. And then when I go through and I evaluate this, and this is a part where we can absolutely use a calculator if you want. This is going to give me an answer of 18 pi when I plug it in. And that's 144 times 1/2 times 1/4, and then we're going to leave it in terms of pi. So just like we were doing when we were talking about radians, if you multiply the pi into the problem, you will get a decimal approximation for this. But what we want to do is try to keep our answers in precise form, because I want an equal sign, not an approximate sign. So 18 pi centimeters squared would be a good way to write this. And then if we wanted to talk about the arc length here, we would use the new formula r theta. And in this case, r is going to, again, be 12. Theta is going to be pi/4. And keeping this in terms of pi, we're really just taking 1/4 of 12, and that's going to give me 3 pi centimeters. Notice that area is in a square centimeter, and arc length is in a one-dimensional unit. So go ahead and pause this video. I would like you to try to find the area of the sector and the arc length for the circle in letter B. Go ahead and pause this right now. All right, welcome back, and here I have the answers for B. And the other thing I forgot to mention prior to having you pause is I wanted to draw a sketch for roughly what that sector looks like. So in this case, the area we're referring to is the amount there. It's going to actually be, actually it's a little less than that. Pi/4 is actually about 45 degrees. So let's actually draw a better picture here. So it's actually going to look more like this. So this is going to be roughly what it looks like. That is going to then be the area of that, and then this is going to represent the length that's right here on the circle. And then 5 pi/6 is almost 6 pi/6, which would have been half the circle. So I kind of just drew it. Think about how we were drawing angles in standard position. Same idea. So this angle is what it approximately looks like. Once again, that's the area, and this is how long this part of the circle is going to be. So we're going to finish this video by just looking at a couple additional applications to see how we can use this in other ways. Example 5 says, if the arc length of a circle is 16 pi units, and then it provides us the radius of 12, so r equals 12, find the central angle that forms the arc and the sector area created by the same angle. So essentially, now I don't know what the angle is, but the idea is that we are being provided this. We are being provided that this is 16 pi. We are also being provided that this radius is 12. So once again, what we're going to be able to do is, since we know the arc length and we know the radius, the arc length formula is just r times theta. I know that my arc length is 16 pi, and I know my radius is 12. So all I need to do to find my theta is divide both sides by 12. And so when I do that, we're going to get an answer of, when I simplify that, 4 pi/3 as my answer. So if we want to better accurately draw what this looks like, let's go ahead and actually draw this. Because 4 pi/3 is going to roughly be a little bit more than half the circle, because 3 pi/3, so let's maybe go about that. So this is probably a more realistic drawing of what this looks like. So now we know that this length here is 16 pi. That was given to us. And we also know that this r here is going to be equal to 12. Now, the second part of this is asking us also to find the sector area. So all we need to do here is use our sector area formula, 1/2 r squared theta. And all we're going to do with that is we're going to go 1/2. R is going to be 12. And now we know theta as 4 pi/3. And so all we're going to do once again is we can throw this into our calculators. I'm going to leave this stuff in terms of pi as much as I am able to. So once again, we're going to get here, when I multiply everything but the pi, we get 96. So it's 96 pi. Now, they didn't give units for this one, so it's just saying the word units. So you can either write unit squared, or whenever there is no specific unit given, you can also just leave it unitless. So let's see where this also takes us. In example 6, it says a 19-inch pendulum swings through an arc of 5 pi over 18 radians. How far does the tip of the pendulum travel? Well, a pendulum works here that if I let go of this, it's going to swing in a circular motion to somewhere maybe around here. Okay? They've given us how many degrees, or I'm sorry, how many radians this angle is going to be. So this is 5 pi over 18. We also know how long the pendulum is. It's 19 inches. So what you may see here is that this is indeed creating a sector. And since this is creating a sector, we are allowed to use arc length because we want to figure out how far this pendulum is actually moving. I want to figure out this length down here at the bottom. So this means that this is going to be an arc length formula. S equals r theta. R is going to be 19, and theta is going to be 5 pi over 18. And we're going to go ahead and we'll throw that in our calculator. Now this one might come out to be kind of a weird decimal if I plug it in. I get 95 pi over 18, which we can absolutely leave that as an answer if we wanted to. That would be inches. If we wanted to see what that approximation was equal to, we could also approximate that in our calculator to be 16.6 inches. And this is the power of writing things in pi form, is that when you have the exact answer, if they ever wanted an approximation, it's a super easy process. You just type it in your calculator, hit your approximate button, and you've got your answer. So it's always nice to have this because you can always create the decimal approximation from the exact answer, but you can't do it in reverse. If you have a decimal approximation, you will now forever lose what the exact answer to that question will be. So that's why we always like to leave things in terms of pi. Here's our last example, and this is actually one I think I would like you to try. There's a couple little challenging pieces in here, but I want you to pause the video and give this problem a try, and then we'll come back in a moment to finish it up. Okay? This is going to be another arc length application, so we're going to use the equation S equals r theta. Now, it says the horse is 18 feet from the center, so right away when I look at my formula, this is going to be equal to 18. The question of the hour is, what is theta going to be? So it completes a revolution every 10 seconds. Well, a revolution is equal to 2 pi radians. So every 10 seconds, I will travel 2 pi radians in terms of an angle. We're doing this over the course of a 2-minute ride. Well, in the course of 2 minutes is equal to 120 seconds. Which means if I'm going 120 seconds around on this ride, and every 10 seconds I'm going 2 pi, well, this is a bit of a unit conversion. One revolution, as we mentioned, is equal to 2 pi. In 120 seconds, we would travel 12 revolutions. Another question is, how many 10s are in 120? How many 10-second intervals are there in that 120? So that's going to be equal to, well, we're going to multiply by 12, and realize that this is going to be equal to 24 pi. 12 revolutions over the course of 2 minutes. So that's what we're going to plug in here. And that was the tough part of this problem, is what theta was going to be. So when we plug this in, we get an exact answer of 432 pi feet. And if we wanted to approximate this instead, depending on the context of the question, we could say exactly how many feet we traveled, and that would be 1,357 feet. So either of these answers would be applicable in this situation. So that is area of a sector and arc length. And now it is your turn to try different problems and applications related to this idea. Thank you as always for watching, and I hope you have a good rest of your day.